This is a diffraction grating problem, and we certainly will use in lambda equal d sine theta. We will rearrange for theta as sine minus 1 in lambda over d. This equals by substitution d is 1 over 250, but we should convert to millimeter if this is millimeter minus 1, so 1 over 250 is in millimeter. To convert millimeter to meter, we should multiply by 10 to minus 3. And we need to convert it because we have lambda here in meter. On your calculator, the answer is it's certainly in columns. Why it is not a meter second minus 1? Simply because it is 2 minus 1. If it was a meter second, it should be also correct, and definitely the question will not give you two correct answers. We simply will multiply the 4,500 milliampere hour by the time, okay? And the time from the question is 1 hour, okay? This is generally for any battery, and for our phone battery, it is also for hour. So we'll multiply here by the time hour converted in seconds, because ampere is in coulomb per second. So the answer will be in coulomb. Okay, we know for an electron that is accelerated under some potential difference, the kinetic energy of it is equal to E times V, and the kinetic energy is equal to B squared over 2M. So if we want V, the accelerating attention, we should first find B and then rearrange for V. We know that B equals h over lambda, so we can simply substitute and take this answer, okay, for finding V. So it is answer we have got squared over 2 times mass of electron times the charge of electron. So as anchor sine C, which is the critical angle, equals N D cladding sine 90, okay, which is 1 for total internal reflection. So ND equals 1.49 for the code times sine 62.4, which is the critical angle, is 1.32. So fiber with large critical angle means that there is fewer total internal reflection, and this means fewer paths for total internal reflection means that modal dispersion decreases and pulse broadening therefore decreases. As the voltmeter reading is 2.6, so we have a current that equals to this voltmeter reading over the value of fixed resistor, which was 47. So I is 0.06 ampere, and EMF, which is also VB, equals to potential across the fixed resistor, 2.6, read by the voltmeter, plus potential across the lamp. And to find it, we have the curve here. We can enter by 0.06, the current, and we will find that the corresponding potential is here. This is 1.5, and this is almost 1.45, because it is between 1.5 and 1.4 and 1.5, so it is 1.45. So for the ionic behavior, we have a linear relationship between I and V. So we'll go for the graph and find where this region of linear relationship, it certainly extends from 0. Okay, if we draw a line here, we can find that it goes away from this linear behavior at the point here, which is almost 0.9. Okay, so we can say that answer is 0 and 0.9. So we have the relation R equals rho L over A as the bar has larger cross section and shorter L, also lower resistivity. This makes the bar has smaller resistance than the wire. Okay, again, we will use R equals rho L over A. So we can rearrange for rho as R A over L. We have R here, maximum resistance that can be obtained, which is 18.3 ohm. And we have A by R squared. We are given the diameter as 0.09, 0.91. So we'll divide it by 2. And as this is in millimeter, we will multiply by 10 to minus 3. All of this squared divided by L. We don't have L explicitly, but we have the coil length, coil in which is a wire is formed, to be 16 centimeter. Okay, and through this length we have 10 circular turns, okay, which has circumference of 2 by r. Okay, again, this is the circumference of each turn, and 10 turns is not the turns through the whole 16. I'm sorry, it is just per centimeter. So if we multiply 10 by 16, we will get all of the terms through the 16 centimeter, which is 160. And if we multiply this 160 by the circumference of a turn, which is 2 by times r, which is this diameter of the turn divided by 2, then we can get it. Okay, so we have 160 total turns times circumference of each turn, 2 by r. I'll convert to meter. Certainly all should be converted to SI because we have here this in ohm. Anyway, we almost done, and we can use the calculator to find the final answer. Perhaps someone may ask why we didn't convert the 16 centimeter, because simply we multiply it by some number per centimeter. So the total number here is useless, and there is no aim from make such conversion. Okay. Inserting unit is ohm meter. We have here in ohm, and This is L over A is in meter minus 1. So this should be ohm meter. So meter times meter minus 1 to be eliminated, and ohm equals ohm, the thing that we talked a lot about for validity of equation. Okay. Y for the variable resistor, if we move the slider, okay, if we move the slider to B, which means is that we almost have no uh, taking length. Y, although we did so, we still have a resistance. We still have a measurement value on the meter. This is certainly because we still have wires for the rest of circuit, and these wires, if long, it will have resistance, and also we have contact resistance, welding two wires or connecting them with banana connector or whatever. This also comes with a resistance. Potential divider. We have two ways of solving this problem. One of them is using the potential divider formula, which is V, potential taken from this part over the total potential, which is that of the EMF 1.6, equating it by the value of resistance, and in this case, this value will be 18.3. I know that someone may say that it is just the maximum resistance, and you are right, because the question will transform to be something like that. Here is a small resistance R, and here is a total resistance taken from this variable resistor. Okay, all of the A, B. This is simply like the one I drew here, still a potential divider problem. So the total R corresponding to 1.6 V will be 18.3 plus the small value of 4.95 ohm. Okay, this gives you V as 1.52 volt. Second method is to use the formula V equals VB minus IR, Ohm's law for the open circuit. And we can here make substitution for V as a value of current times the total resistance, sorry, maximum resistance 18.3 for VB 1.6, and again it is value of I times 0.95. You can solve this equation for I. find I, and then substitute to find V. Okay, energy levels, why they are negative? Because energy required to ionize the atom and when ionization happens, energy level is 0. So ionization level at which the electron will be when ionization occur is at E equals 0. So shortest wavelength is the highest frequency or the highest energy. Okay, so we need the transition that gives us the higher delta E, so it should be between the very high and the ground one. So should be from this level to here. Okay. And to calculate the wavelengths, we'll first calculate delta E. Delta E is the difference as we have just said, and it is here is 5 very small squares. Each one represents 1/5, which is 0.2 eV. So we have this value, you can say -2, -2.2, -2.4, and -2.5, or if you read from low to up, so it is -3, -3 plus 0.2, which will be -2.8. Okay, and here is a 2.6, here is a 2.4, all in minus certainly, so still this value is a red from up to blue or from down to up would be -2.5. We can say that we have -2.5 minus 10.4, and we will get the answer as 7.9. EV. We then have A equals HC over lambda. So we can rearrange for lambda as HC over A. we have here 7.9 electron volt means to multiply by 1.6 times 10 to minus 9 to convert to joule, because this is in SI, this is in SI, so conversion is a must. And okay, next question. How mercury atoms become excited in fluorescent tube? So firstly, we have electrons emitted by or from electrodes are accelerated by the potential difference applied between the electrodes. Then they collide and transfer some of their energy, their kinetic energy, to the mercury atoms. So we have accelerated electrons from electrodes, collide and transfer kinetic energy with mercury atom. Here is explain how excitation leads to emission of white light. So mercury atom de-excite and emit UV photons, which are absorbed by the coating powder atoms. Atoms of coating powder absorb this UV, which in turn excites, I mean the atoms of the coating powder become excited and de-excite and emit visible photons. And these visible photons are with different wavelengths, which combine, the different wavelengths combine to white light. Okay. Anytime you can pause the video to read the question carefully before resuming for the answer. So we can simply replace lambda by C over F because we don't have lambda, and all these values are given. Frequency here 11 mega, sorry, 11 gigahertz, and the distance, I think it is given here in the diagram, 75, or after conversion, 4.75, and for S, this is between slits, it is 9.5 centimeter, or 0.095. So W would be 0.215 meter. Why this equation is not accurate? Because D, which is the distance between the bubble slit and the screen, should be too much greater than S or lambda. Okay, we have here a lambda. If you calculate it separately, you will find that it is 0.027. Okay, and this is in meter, which means 2.7 centimeter, and the distance D is 75 centimeter. So although it seems to be too large, but it should exceed 100 times at least, and 70 for 2.7 or almost 3. The ratio here is less than 100 times. Okay. Same certainly goes for S, which is 9.5 centimeter, almost 10 centimeter. So although D is 7 times greater, but this is not enough. As I said, it should be at least 100 times greater. Okay, rotating the area from 0 to 360. You want the relationship between intensity and angle of the Earth. So as the radiation is vertically polarized, so we expect that intensity drops to 0 when the angle between the area and the waves is 90 degrees. Okay. So when the angle is 0, which means there is a parallel or anti-parallel orientation between the area and the radiation should be maximum. And when this angle goes to 90 degrees, say the area is here and the waves is vertical like this, so the intensity should drop to 0. Okay. Again, it will comes up to maximum as the area rotate to a vertical position again, and so on goes to 0 when it becomes horizontal, and then again to maximum when it becomes vertical. So a simple explanation is when area parallel to vertically align it. Microwave intensity is the highest, and when area is perpendicular, then it has zero intensity. Okay, we need here a new drawing for relation between I and angle, but in this case we have angularized microwave. So whatever the angle between the area and the source, we will have intensity. Okay, but as the plane of microwave is not only vertical, it is angularized, so it is in all direction. We expect that the intensity not to be maximum, but to be the average. Okay, so we can make some counting here. Here is the 4 squares, and here is another 4 square. So this is the average. We should certainly make the labels A and here B.